Okay, so it's page 9. So today we will start to learn about differentiating functions without using those first principal formulas. But we will do this first one using the first principal formula, and then we'll make some connections. So we saw yesterday that when you find the derivative, it's the same as finding the slope of a tangent line to a curve at a certain point. It's also the same as finding the instantaneous rate of change of an object as it's changing with respect to some variable. And so we said that we could use those limit formulas, and yesterday we used the one involving h, and we said that we could find the derivative by taking the limit as h approaches 0 of f at a plus h minus f at a all over h. The limit as h approaches 0. And then we said, well, instead of using the variable a, which is what the formula has, we could replace the a with the x so that we have the same variable. So instead of f at a plus h, it would be f at x plus h, meaning the x here would be replaced with x plus h. But I can't forget to write the limit there. So it'll be x plus h all squared plus 2 times x plus h minus 3 minus, instead of f at a, it would be f at x all over h. So we need to do something to get rid of that factor of h on the bottom because it is non-permissive. So x plus h squared would be x squared plus 2xh plus h squared plus 2x plus 2h minus 3 minus x squared minus 2x plus 3. And we've got some terms that are going to cancel here. The positive x squared minus x squared cancels. The positive 2x minus 2x cancels. The minus 3 plus 3 cancels. So we're just left with 3 terms on top, and they all involve the variable h. So what I'm going to do is I'm going to take out a common factor of h on top. And you don't necessarily have to do that. You could just simply divide all remaining 3 terms by h, and it would cancel with the h in the bottom, but this is the same thing. And so you're left with the limit as h approaches 0 of just 2x plus h plus 2. And when h equals 0, this is just going to be 2x plus 2. So there is the derivative. So again, this would be an expression we could use to find the slope of the tangent at any point on the curve x squared plus 2x minus 3 by taking the x value from that point and subbing it in. But let's start looking at making some connections here. You also might remember from yesterday that we did one example where f at x was just x squared, and we saw that f prime x was 2x. That was one of the ones we did yesterday. The derivative of x squared is 2x, and in this case, the derivative of x squared plus 2x minus 3 is 2x plus 2. So here's what we see. The derivative of a constant term is always 0. Okay? So if we look at x squared plus 2x minus 3, the derivative of the x squared term is 2x. Again, it's the same as what I wrote above here. We saw that one yesterday. So you see this 2x comes from taking the derivative of x squared. This plus 2 in the derivative comes from taking the derivative of 2x. That's where the plus 2 comes from. And if we add a 0 on the end of this, we would say that that 0 comes from the derivative of negative 3. Negative 3 is the constant. So that is what that first statement says. The derivative of a constant term is always 0. Second statement says the degree of the derivative of each term is 1 less than the degree of the corresponding term of the function. That is also true. The derivative of x squared is 2x. Right? The term in the original function is degree 2. The term of the derivative is degree 1. Right? The derivative of 2x is just plus 2. Same thing. The term has a degree of 1. The derivative term has a degree of 0. Okay? So that is also true. But here's what we really use in order to determine the derivative of each term. The coefficient of the derivative of each term is the product of the coefficient and the exponent of the corresponding term in the original function. Yes. Can't hear you. Yes, but it's still degree 0. The degree is the power or the exponent on the term, on the variable. It's a degree 0. Yes. Anything to the power 0 is 1, but we're talking about the degree. It's degree 0. So again, the coefficient of the derivative of each term is the product of the coefficient and the exponent of the corresponding term of the original function. So if we go back up here, okay, the exponent on x squared is 2, the coefficient of that term is 1. What you really do is you multiply the exponent by the coefficient. 2 times 1 is 2. And then, remember we saw and talked about the fact that the degree of the derivative is 1 less than the degree of the corresponding term from the original function. So when you multiply the 2 by the 1 in front, this power decreases by 1. The degree goes down by 1. So you see 2 times 1x is 2x. That's where this first term of the derivative comes from. The second term of the original function is 2x to the power 1. So again, you're going to multiply the exponent by the coefficient. 1 times 2 is 2, and then the power on x, again, decreases by 1. So it'll be 2x to the power 0, or just plus 2. And again, this minus 3 is minus 3x to the 0. We can use the same law. Multiply the 0 times the negative 3 in front, which will give you 0. So it doesn't really matter what the power is. Technically, it would be negative 1, but when you have a 0 in front, 0 times anything is 0. So this is known as the power rule for derivatives. If y equals a times x to the n, then dy by dx, remember that's one of our notations for derivative, can be found by multiplying the power, the exponent, by the coefficient in front. So it's n times a times x, and then the power decreases by 1. This is what we use to find the derivative term by term for any polynomial function. And it doesn't even have to be a polynomial. You can have negative exponents there as well. And the same rules apply. So as long as it's not a expression where it's a product or a quotient or something raised, some polynomial raised to a power or an expression raised to a power, as long as it's not one of those, then we can use this rule to find the derivative of that expression. And you just do it term by term, and this is what this is saying. The sum rule says that the derivative of f at x plus g at x is the derivative of the individual functions added together. So you can talk about this instead in terms of two different functions added together, or two separate terms, or three separate terms, or four separate terms, whatever, added together. You just simply take the derivative of each term or each function separately. And the same thing if they're being subtracted. It doesn't matter. You take the derivative of each term separately by following that power rule for derivatives. So, number one, we're going to differentiate these. If f at x equals 2x cubed plus 4x, then f prime x, the derivative, can be found by this power of 3 is multiplied by the coefficient of 2, and then the power decreases by 1. The 4x is 4x to the 1, so the exponent 1 is multiplied by the 4 in front, and then the power on x decreases by 1. Now, you don't have to show this step, just writing it out to make sure you see how it's done. So you're going to have 3 times 2, which is 6x squared plus 4. There's the value of that derivative, or the expression for the derivative. You just do it term by term. If y equals this expression, then dy by dx. So notice the first one was f at x equals, so to show that we're taking the derivative, it's f prime x. The second one, it's y equals, so we write dy by dx, the derivative of y with respect to x. So the 3 exponent is multiplied by the 7 in front, and we'll get 21x squared. Remember, the power decreases by 1. The exponent 2 is multiplied by the 12 in front. It becomes plus 24x. The power decreases by 1. This minus 3x is 3x to the 1. 1 times negative 3 is negative 3. And the power decreases by 1. So it would be x to the 0, which we don't need. Yes. You can do fourth derivatives, fifth derivatives, sixth derivatives. There will be times where we will take the second derivative for one of the applications we'll learn about. But you can keep going until you get down to a constant, and then when your next derivative will be 0, because the derivative of a constant is 0. So yes, we could do the second derivative of this, which would give us a first degree equation, and then we did the next derivative, which would just give us a constant, and then the final derivative would just be 0. Now, question 3 right now is expressed as a quotient. We haven't learned how to take the derivatives of a quotient. So in most cases, we look at it and see, can we simplify it first? Can we divide each term on top by the one on the bottom? And we absolutely can. If you divide the 3x to the 4th by x, it'll become 3x cubed. If you divide minus 2x cubed by x, it'll become minus 2x squared. And the constant term of 5, remember, that's the same thing as 5x to the power 0. So you can still divide. 5 divided by 1 is positive 5, x, and then when you divide the x to the 0 by x to the 1, remember you subtract the exponents, keep the base the same, 0 take away 1 is negative 1. So this one is not classified as a real polynomial function because polynomial functions must have exponents that are whole numbers, okay? And that last term has an exponent as an integer. But it doesn't matter. You can still take the derivative using exactly the same processes that we've been doing. So dy by dx would be 9x squared minus 4x minus 5x to the negative 2. Remember, the power always decreases by 1. And you could leave it like that. Normally, we don't leave terms with negative exponents, but that is an expression for the derivative. So if you're checking answers in the back of the book, what they might do is make the exponent positive by moving the x to the negative 2 down to the bottom. And then what they also might do is get a common denominator, which would be x squared, so that you can write this all together as one rational expression. So the denominators on the first two terms right now are only 1, so you need to multiply bottom and top by x squared to get a common denominator. When you multiply 9x squared by x squared, you'll get 9x to the fourth minus 4x times x squared is 4x cubed minus 5 all over x squared. So again, if I was marking an assignment or a quiz, I would accept that step there that I've underlined. But if you're checking answers in the back of the book, they might go on and get a common denominator, because in math normally we don't leave answers with negative exponents. Okay? Question 4. Before I differentiate, the first term is already written as a power. I would want to do the same thing to the second term, write it as a power. The root of x is the same as x to the half. And then I use the same process. If y equals the function, then dy by dx will be the expression for the derivative. So the exponent 4 multiplied by the 2 in front gives us 8x cubed. With this, Ben? Checking your stocks again? Yeah, is it up or down? Oh no. Now's the time to buy more. So same thing with that last term. Follow the same rule. The 1/2 exponent comes in front and multiplied by the coefficient of 1 that's in front of the x. And then the exponent of 1/2 is decreased by 1. When you take 1 away from a half, you're going to get negative a half. Right? So technically that is an expression for the derivative. Now again, if you were checking answers in the back of the book, they may do a couple things. One of them would keep the 1 on top. The x would go down to the bottom with the 2, and that would make the exponent sign positive, positive a half. And we know that positive a half means square root, but it's only on the x, not the 2. So it's 8x cubed plus 1 over 2 root x. And normally we don't leave answers with radical denominators, so the other thing that you might do is just take that term and multiply top and bottom by root x, which gives us 8x cubed plus 1 root x, or just root x over 2x. And finally, what they might do is combine these two together by getting a common denominator of 2x. The 8x cubed has a denominator of 1, so bottom and top would have to be multiplied by 2x, which would give us 16x to the fourth plus root x all over 2x. So again, if you were checking answers in the back, this is something that they might do. Okay? I said that we're going to learn about rules for taking the derivatives of a product, derivatives of a quotient, as well as derivatives of something, some expression raised to a power, which is what we have right here. But we haven't learned about those rules yet. So right now we're going to simplify, which is what we've been doing. Simplify first. So to square a binomial, you can square the first term. You can multiply the two terms together, which would give us 2x root x and double minus 4x root x. Actually, hang on a second. That's not right. Let me fix that. And maybe what I'll do, I know what I'm going to do. This will make it a little bit easier. I'm going to just change the way that second term looks by writing it as x minus 2x to the negative a half. Right? Root x means x to the half, and then move it from the bottom up to the top. And this is the expression I'm going to square. by squaring the first term, which will be x squared. To get the middle term of the expansion, we multiply the two terms together and double. So if I write this out, when you multiply the two terms together, you're going to get a coefficient of -2. When you double, you're going to get a coefficient of -4. And also, we're multiplying the two terms together, so it also means we're going to multiply x times x to the -half. So that's what you get when you multiply the two terms together and double to get the middle term of the expansion. So I'm going to simplify that, but this is just kind of showing step by step what we're doing. And then you square the last term. When you square the -2, you're going to get +4. And the x to the -1/2 also has to be squared. So that's what I'm showing. Square the first term, multiply the two terms together and double, and then square the last term. So my last step before I differentiate is to simplify that expression. So I've got x squared. Then I've got -4x to the 1/2. When you multiply x to the 1 by x to the -1/2, you add the exponents. Keep the base the same. 1 plus -1/2 is +1/2. And then for that last term, you're going to have +4x to the -1. When you have one exponent raised to another, you multiply the exponents and keep the base the same. So there's our expression simplified. We simplified it first because we haven't learned how we differentiate quotients. We haven't learned how we differentiate when you have an expression raised to some power. So now we can take the derivative. And f prime x is found by taking the derivative of each term. The derivative of x squared is 2x. To get the derivative of the next term, we multiply the exponent 1/2 by the coefficient in front, -4. So 1/2 of -4 is -2, x to the -1/2. And then -1 times 4 is -4x. And remember that the power decreases by 1. So there's an expression for the derivative. And again, what they might do, x to the -1/2, you can move that to the bottom. It becomes x to the +1/2 or root x. And 4x to the -2 would be 4 over x squared. And you could get a common denominator, which would be x squared for all three of those terms and combine them into one expression if you wanted to. So what would that look like? Well, we said our common denominator would be x squared. So the 2x's over 1, you'd have to multiply top and bottom by x squared. It would become 2x cubed. This root x is the same thing as x to the 1/2. So if I just write this on the side here, if I want x to the 1/2 to become x squared, I would have to raise that to the power 4. Because when you have one exponent raised to another, you multiply the exponents. 1/2 of 4 is 2. So to make x to the power 1/2 become x squared, we'd have to raise it to the power 4, which means we have to raise or multiply top and bottom. Basically, I guess that's not right. What I said is correct, but we can't really do that to this. Instead, what I would have to do is multiply it by some power of x. And remember that you want the power to be 2, which means I'd have to multiply by x to the 3/2. So that's what I would have to do. Because when you multiply powers with the same base, you add the exponents. And when you add those exponents, you're going to get 4/2, which is 2. So you need to multiply top and bottom by x to the 3/2. So this 2 we multiplied by x to the 3/2. And that last term already has our denominator of x squared. So essentially you're multiplying top and bottom by 1. And you can use, well, I guess you can't use your graphing calculator because you can't use it for a quiz or test, but for an assignment you certainly could. If you put this expression we got for the derivative in the calculator and then put our simplified expression in, they should give us the same graph. So on an assignment, you could use your calculator to check this. So our original expression for the derivative was 2x minus 2x to the power negative 1/2 plus 4x to the power negative 1. Oh, that should be negative 2, not negative 1. I was looking at the line above. So 2x is right, minus 2x to the negative 1/2 is right, minus 4x to the negative 2 is right. So we can see what that graph looks like. Well, when I put our simplified expression in, I would use brackets to keep the numerator together. 2x to the power 3 minus 2x to the power 3 over 2 minus 4, all in brackets, divided by x squared. So when I graph this, it'll happen quickly. Yeah?
Plus 4x to the negative 2.
Oh, thank you. That will make a big difference. I checked the terms, but not the signs in between. Okay, so there we go. Happened really fast. It graphed the first one and then the second one directly over top the first. So that just shows that the simplified expression is equivalent to what we started with. So as we've seen, one of the applications of the derivative is to find the slope of a tangent at any point. Instead of using those first principle formulas, we can now use what we've learned about taking derivatives. So Brighton, what's the derivative of that expression? You want to bet a pop on that? Time's up. Should have said yes because you were right.
Should have been more confident.
Yes, you should have been more confident.
Bryson, you missed an opportunity.
I've got a 2-liter bottle of Dr. Pepper sitting at home, just itching to be given away.
Okay.
All right, so there's our expression for the derivative, and you can use it to find the slope of the tangent at any point along that curve. We want to find the slope of the tangent at positive 2. So I'll change my notation to say f prime 2 would be 10 times 2 take away 2. 20 take away 2 is 18. That's the slope of the tangent to that curve at the point x equals 2. So it's a fairly steep line. And we also want to find the equation. And to do that, we have to also know the y value because we want to know the point of tangency, not just the x value, but the y value as well. So let's find it. Y equals 5 times when x is 2. 2 squared minus 2 times 2, take away 12. 2 squared is 4 times 5 is 20. Take away 4, take away 12. So that'll be positive 4. 16, take away 12 is 4. So our point of tangency is the point 2, 4. And remember, we saw 2 different ways to find the equation. You can use y equals mx plus b. We know that m, the slope, is 18, and we can also use the point 2 comma 4, meaning y is 4 when x is 2, m, the slope is 18, and you can determine what the b value is, which represents the y-intercept, by solving for b. When you subtract 36 from both sides, you're going to get negative 32. There's the y-intercept. So our equation would be y equals 18x minus 32. That is the equation in slope-intercept form. In general form, it would be 18x minus y minus 32 equals 0. Okay? This next one is very straightforward. It's done exactly the same way. So I'm just going to skip it and go on to this question. Find the equation of the tangent to the curve 2x squared plus 3x minus 1 that is parallel to y equals 2x plus 1. So in the previous one, we were given the point of tangency. In this case, we have to first figure out what the point of tangency is. Remember, the derivative will give you the slope of the tangent line. So if I take dy by dx, that will be 4x plus 3. That's an expression for the slope of the tangent. We need to figure out at what point along the curve will our tangent line, and that tangent line will have a slope that is defined by 4x plus 3, but where on the curve will that tangent line have a slope of 2? So normally we would use this expression to find the slope of the tangent, but in this case, because our line is parallel to the line y equals 2x plus 1, it would have the same slope as the line 2x plus 1, and that line has a slope of 2. It is in slope-intercept form. So to find where in the curve our tangent line will be parallel to 2x plus 1, it's where the slope equals 2. This is an expression for the slope, 4x plus 3. So now we're going to solve for x. This will tell us where the point of tangency is. The point of tangency would have to be where x equals negative 1/4. Again, the derivative gives you an expression for the slope of the tangent, which we know must be parallel to 2x plus 1, so it must have the same slope as 2x plus 1, which is a slope of 2. So like we did before, we're going to need to know what the y value is at the point of tangency. We now know the x value is negative 1/4. We need to find the y value there. Negative 1/4 squared is 1/16. Times 2 would be 2/16 or 1/8. Minus 3/4 minus 1. So if we get a common denominator of 8 here, it'll be 1/8. Take away 6/8 minus 8 over 8. 1 take away 6 is negative 5. Take away 8 would be negative 13/8. So this is our point of tangency. Our point of tangency is at the point negative 1/4 comma negative 13/8. And remember, we've seen a couple different ways that we can find the equation of the tangent line. In the last example, we use slope-intercept form, but we also have point-slope form. Which is that. Remember, most equations have variables x and y in them. And so that's where the x and y in this equation comes from. X1 and Y1 will be the x and y coordinates at our point of tangency, and m, our slope, we know is positive 2. So y minus negative 13/8 would become y plus 13/8 equals m, the slope. X minus negative 1/4 will become x plus 1/4. So technically that is the point-slope form of the line. That is the point-slope form. but you might be asked to write it in general form or standard form, which means the same thing. So you'd have to multiply out the brackets on the right, and then one of the other things about general form is you can't have any fractions. So we'd have to multiply all the terms by the common denominator, which would be 8. So the first term multiplied by 8 would be 8y. That second term multiplied by 8, they would cancel, you're left with 13. On the right side, the 2x times 8 would be 16x, plus the 1/2 times 8 would be 8 over 2 or 4. And then we make it equal to 0. And normally general form is written with the x term being positive, which means we're going to move everything from the left over to the right. So the 8y will become negative, and when you subtract 13 from both sides, you'll get negative 9. Okay? So there's the equation. This next one says, find the equations of both lines that pass through the point 2, 9 that are tangent to the parabola y equals 2x minus x squared. So let's just draw a little graph of this just to see what we're working with. The parabola is 2x take away x squared, which is the same thing as negative x squared plus 2x. So that's a parabola. It opens downwards, remember, because our initial term coefficient is negative. How do we find the x-intercepts, Brighton? We find the x-intercept by setting it equal to 0 and then factoring. Taking out a common factor of negative x gives us x minus 2. And so our x-intercepts are at 0 and 2. So if we graph this, it's going to open downwards. It's going to have x-intercepts of 0 and 2. So if I say this point here is positive 10, this point here is positive 5 on the y-axis, my x-axis, I'm going to use a scale of 1. Our quadratic has, again, x-intercepts of 0 and 2. It's going to open downwards. We don't know exactly where the maximum point is, but we could find it quite easily. It would be where the x value halfway between the two x-intercepts. And these quadratics are always symmetrical about the axis of symmetry. So the axis of symmetry, halfway in between the two x-intercepts, which would be at positive 1. And if you let x equal positive 1 in the equation, you're going to get 2 minus 1, which is just 1. So that's where our vertex would be. So this quadratic would look something like this. And what we're asked to do is find the equations of the two tangent lines from the point 2, 9 to this curve. So the point 2, 9 would be up here somewhere, and there would be two tangent lines. One would come something like that. The other one would come something like that. That's what we're trying to find here. So similar to the last one, yes. You just said the same line, but with different slopes, so that makes no sense. No, they're two different lines. They are two different lines. If you look at these two lines, you can obviously tell that the one on the right is going to be steeper than the one on the left.
I don't know, let's say we only use the one flat, or one we said we always very hot, the other was
It's not the way it works. Okay? So, we want to find the points of tangency. We're going to use an expression for the points of tangency. And those points of tangency we would write, in general form as x comma y, but remember y is 2x minus x squared. So this is an expression for our 2 points of tangency. X comma 2x minus x squared. And this point up here is the point 2 comma 9. Remember that the slope formula can be used to find the slope of any line as long as you know x1, y1, x2, y2, which we actually have in this case. Okay? The slope of the tangent m equals y2 minus y1 over x2 minus x1. So if I say the point of tangency is 0.2, it doesn't matter which one I use because they're the same expression, and the 0.2 comma 9 is 0.1, I can write an expression for the slope of these tangent lines in terms of x. So y2 minus y1 would be 2x minus x squared minus 9 over x2 minus x1 would be x minus 2. So that's one expression for the slope of those tangent lines. But also remember that you can also get an expression for the slope of a tangent line to any curve by taking the derivative of that curve. So m also equals dy by dx, the derivative, which would be 2 minus 2x. So that's also an expression for the slope of the tangent lines. And so these two expressions have to equal each other. They both represent the slope of those tangent lines, right? The first expression we got using the slope formula. The second expression we got by taking the derivative, which we know also gives us the an expression for the slope. So those two expressions have to equal each other. 2x squared, excuse me, not 2x squared, 2x. 2x minus x squared minus 9 all over x minus 2 has to equal 2 minus 2x, or 2 minus 2x over 1. And we're going to solve this equation to find out where x is, which will be where the point of tangency is. We're going to solve this equation by multiplying both sides by x minus 2, which is the same as cross multiplying. It's the same thing. So 2x minus x squared minus 9 has to equal x minus 2 times 2 minus 2x. So when I multiply this out, the front terms will be 2x, the outers will be minus 2x squared, the inners will be negative 4, and the last will be positive 4x. If I bring everything from the right side over to the left, I'll add 2x squared to both sides, which will give me x squared. On the right, 2x and 4x gives us 6x. If I subtract the 6x from both sides, I'll get minus 4x. And then when I add 4 to both sides, I'll get minus 5 on the left. And we can solve that quadratic by factoring. So again, I'm solving the quadratic x squared minus 4x minus 5. The factors there would be x minus 5, x plus 1. So x equals 5 and negative 1. Which, if we look at our graph at the top, x equals 5 will be the point of tangency on the right. X equals negative 1 will be the point of tangency on the left. Those are the x values at the point of tangency. So we've seen that if we're going to write the equation of the tangent line, we also need to know the y values at those points. So f at 5 would be 2 times 5, which is 10. Take away 5 squared, which is 25. So that is the point 5 comma negative 15. And then f at negative 1. 2 times negative 1 is negative 2 minus negative 1 squared. So negative 2 take away 1 is negative 3. So that is the point negative 1 comma negative 3. There's our 2 points of tangency. So the other thing we need to do is we need to find out what the slope of the 2 tangent lines are. Okay? And we'll do that by taking our expression for the derivative, which is 2 minus 2x, and find out the value of that function at positive 5. So f prime 5 means the value of the derivative, 2 minus 2x, 2 times 5 is 10. So that line on the right has a slope of negative 8. The line on the left, the value of the derivative when x equals negative 1, will be 2 minus 2 times negative 1. That becomes 2 plus 2, or positive 4. Again, that jives with what our graph does. Right? The line on the left has a positive slope. The line on the right has a negative slope. The line on the left, you can tell by looking at it, is less steep. Right? So everything jives with what the sketch is telling us. So now we just have to write our 2 equations. So let's first do the equation of the line on the left, which the point of tangency is negative 1, negative 3, and the slope is positive 4. So this will be line 1. Again, that's the one on the left. So if I use y equals mx plus b, right? The point of tangency is negative 1, negative 3, and the slope is 4. So negative 3 will equal negative 4 plus b, and when you add 4 to both sides, b will equal 1, and that equation will be y equals 4x plus 1. So that's the equation in slope-intercept form. And if you wanted to write in general form, that's easy to do. Right? Line 2, that's the one on the right that goes through the point 5 comma negative 8. Sorry, not 5 comma negative 8. 5 comma negative 15. And the slope is negative 8. I apologize, it's not 5 negative 15. Yeah, the one on the right, I'm sorry. That is correct. With the slope of negative 8. So Negative 15 is our y value, m the slope is negative 8, x the value is 5, so negative 15 will equal negative 40 plus b. If you add the 40 to both sides, b will be 25, and the equation will be y equals negative 8x plus 25 in slope-intercept form. So like the last example, we're not given the point of tangency, we have to figure it out. So a bunch of algebra there to do that. And this next one is exactly the same. We've got a curve. We want to find the equation of the two tangent lines that pass through the point 0, negative 5. It's done exactly the same. I guess except the difference here is that we're given our point. No, we're not. We're not giving our point of tangency, so it would be the same. Okay, exactly the same method. So I'm going to stop there. Page 88, numbers 1, 3, and 6 through 9. I am going to collect this one for marks. So you need to do it, and you need to hand it in. Okay, this one is due for marks.